So hi everyone. Oh, sorry. Have you? Okay. Hi everyone. I'm Nathaniel, and I'm happy to present you our work on QVM, Quantum Gate Virtualization Machine, which I did together with Giortamis and Professor Bhatotia at TU Munich and Leibniz Supercomputing Center. So, as you all know, quantum computing promises to solve lots of hard problems across a range of applications in areas like material science, quantum chemistry, cryptography, or maybe even machine learning. And to allow us to do these quantum computation, we have also seen rapid development of quantum processing units, or QPUs, with companies focusing on superconducting circuits, ion traps, or recently neutral atoms to realize such quantum processing units. When we talk about quantum programs, so programs that can actually run on these quantum QPUs, we've already seen, we talk about the quantum circuits, which can be represented as this assembly format that you can see on the left, or as a nice circuit diagram as you can see on the right. When we do a quantum computation, we always start by initializing some qubits, followed by doing some operation as gates, which are single qubit gates or multi-qubit gates that change the state of these qubits, followed by, in the end, a measurement to get some information about the state of the qubit after our computation. When we talk about quantum programs that are actually useful for solving real problems, we are interested in two main metrics of these quantum circuits, which are the width, so how many qubits we can execute our circuit on, as well as the depth, so how many operations we can do after each other on the quantum circuits. And real-world application need to run really deep and wide quantum circuits. So, of course, we haven't seen any significant breakthrough in quantum computing yet, so why are these metrics still limited? So width is, of course, limited by the number of physical qubits that we can put on our quantum chips, and depth is limited by the error per operation of our operations on the QPUs, as every operation introduces some noise to the computation, such that these errors propagate through the circuits and get larger and larger, such that we have an increasing chance of failure of our computation at the end of the circuit. So to put this finally into perspective, where we are right now, we are in this era of QPUs, where we have QPUs of hundreds of qubits and error rates of 1 or less than 1%. And you would need to go somewhere here to do some meaningful, or it is believed that we need to go somewhere here, which means that we have to do an orders of magnitude improvement in both the number of physical qubits and the error rates per operation. So how can we get there? One promising solution that has been around now for a while that could help us get there is a solution called gate virtualization, which allows us to virtualize 2 qubit gates as a combination of single qubit gates. So as you can see here in this example, we have a circuit on the left where we have a 2 qubit gate in the middle. And what we can do is we can write this as the same expression on the right, where instead of the 2 qubit gate, we run some circuit instantiations I, where we insert some single qubit gates instead, which in this case allows us to actually run these circuit instantiations as 2 independent subcircuits. And then in the end, we need to do some classical reconstructions to get the same result as if we had executed the circuit on the left. So gate virtualization has 2 opportunities that we can utilize theoretically for scaling depth and width, which are circuit cutting and dependency reduction. So circuit cutting is very helpful if we have some large quantum circuit and we want to run this on a small QPU, which in this case, of course, doesn't work since we have more qubits in our circuit than in our physical QPU. So what we can do is we can just virtualize this gate in the middle, allowing us to decompose the circuit into multiple smaller subcircuits, which now fit easily on the smaller QPU. Dependency reduction is very helpful if we want to minimize the error propagation in the circuit. So in this example, we have a small circuit here, and we can imagine that some error will happen here at the beginning of the first qubit. So what will happen is actually this error will propagate theoretically through the entire circuit due to the dependencies between those qubits and operations, leading to errors on every qubit at the end of the computation. However, if we now decide to virtualize this gate, what would happen is that an error occurring on the same qubit will now only propagate to 3 qubits, so that the third qubit here is actually independent of this error, which allows us to construct more circuit with more depth as we have less error propagation. So circuit cutting has a potential for us to gain more width in quantum circuits and dependency reduction for more depth. However, gate virtualization, of course, doesn't come without costs. So actually, it has some overheads, which can be illustrated right here. So if we want to virtualize some k gates in our circuit, what we need to pay is quantum processing cost of 6 to the power of k subcircuits that we need to run. And we need then to also post-process these results classically using 6 to the power of k floating point operations. And these values come from theory, so you have to believe me on that. So unfortunately, we have some high exponential quantum classical overheads that we need to get around. So to recap, we've seen that gate virtualization has strong potential in scaling depth and width of circuits, but it also has these super high exponential overheads, unfortunately. So in this work, we ask ourselves, how can we still leverage gate virtualization to do some gate virtualization before the overhead gets too large, to still leverage this to scale our depth and width. So to this end, we proposed QVM, which is a system to use gate virtualization for scalable and reliable executions for circuits on disk QPUs. And we made 3 core contributions, which are: first, we allow for a programmable and efficient gate virtualization by coming up with a small IR to do efficient analysis on the circuits and apply virtualizations. Secondly, we try to apply optimal gate virtualization by coming up with a compiler, a small compiler that applies those virtualizations to circuits. And finally, we try to virtualize as many gates as possible with our QVM runtime, which allows for a parallel execution of both quantum sites and classical post-processing. So now, after motivating the program, let's look at how the system looks like. So this is kind of where we are, where we want to execute some large quantum circuit, but we only have some small QPUs and some classical nodes at our disposal. So for running this circuit, QVM comprises of 2 main components, the QVM compiler and the QVM runtime. So if we now pass the circuit to execute, what would happen is we pass it first to the front end, which emits some virtual circuit IR, which gets passed to the optimizer, which has 3 main optimization passes: the circuit cutter, dependency reducer, and qubit reuser. After optimizing this IR, we pass it to the code generator, which generates some QPU-optimized virtual circuit. To run the virtual circuit now, we pass to the QVM runtime, which comprises of the virtualizer, which is the main brain of virtualizing quantum 3-qubit gates. And it has the instantiator, which is for instantiating these different subcircuits, as well as the knitter, who does the parallel processing on many classical nodes, as well as the instantiator uses a scheduler to schedule quantum circuits on many small QPUs in parallel. So yeah, the talk I will focus on these 2 main optimization passes, starting with the circuit cutter. So the circuit cutter, we need to solve an optimization problem, having the constraint that we want to cut the circuit into multiple subcircuits with a size S, which could be a QPU size. And we have a budget B of a maximum amount of gate virtualizations that we can do, so to constrain kind of the overhead. So our goal is to cut the circuit into subcircuits with smaller than S qubits with not more than B virtual gates. So to this, we use a qubit graph, which is in our virtual circuit IR, which models kind of this qubit connections, where the vertices are qubits, and we have an edge between 2 vertices if there is a 2 qubit operations between those 2 qubits. So for example, if we have here between the qubits 3 and 4, we have 2 qubit operations, leading to us having an edge between those 2 vertices with a weight of 2, since we have 2 qubit gates. So to do these optimizations, so here we want to cut to 3 qubits subcircuits, and we have a budget of B equals 2 virtual gates. So what we will do is we take this graph and we will do some partitioning of the circuit using our favorite gate partitioning algorithm to minimize the weight of cut edges and to kind of fulfill these constraints. So this would lead us to virtualize these two qubit gates right here, giving us the virtual circuit on the right, which fulfills the constraints that we had in the beginning. So let's talk about the dependency reducer. So for the dependency reducer, we also need to find a solution to an optimization problem where we have the constraints that we have some budget B, and we want to minimize the operation dependencies. So here we use the operation graph of our visual circuit IR, which models the dependencies of the gates, where we have vertices being 2-qubit gates, and an edge between two vertices if there is a direct dependency. So here there's a direct dependency between gate 1 and gate 5, such that we have an edge between those two vertices. And what we do here is we take our dependency graph and we try to find the optimal nodes to remove from this graph to minimize the dependencies, which we can do, of course, optimally, or a good heuristic is also to just remove central nodes in the graph. So this would lead us then to virtualize this gate in the middle, giving us this dependency graph and giving us this new virtual circuit, which reduces the operation dependencies in this circuit. So finally, let's talk a bit about the results of our paper. So we have implemented a prototype of this system in Qiskit, and we try to focus on two main research questions of the impact of the circuit cutter and dependency reducer, but we have many more results in the paper. And we compared to Qiskit, and we actually did the experiments on real quantum hardware with the IBM Perth and Kolkata devices, and benchmarked on many NISQ applications. So here for the circuit cutter, we tried to compile to 7 qubit subcircuits, and we measured the fidelity of, so how good the result is of running the circuits, where higher is better, and we did this for 10 and 14 qubits. And we had two main setups, so the small QPU with QVM and the large QPU with QVM and the baseline. And note that we cannot even run the baseline on the small QPU since we have more qubits, so 10 and 14 qubits, so more than actually would fit on the small QPU. So we can see that on the same machine, we vastly outperform the baseline with our approach, and sometimes even on the smaller and worse machine, we also outperform the baseline, while being sometimes the same or worse. So we can effectively double the circuit width while maintaining or sometimes even improving fidelity. And the dependency reducer we compiled, I think in the interest of time, I can just say that we also minimize the qubit dependencies and relative circuit depth using our dependency reducer by 50% almost, such that we have a 1.7 times dependency reduction, leading to a 1.6 circuit depth reduction. So to conclude, we've seen that gate utilization is promising to scale depth and width of quantum circuits. However, it's quite complex and limited due to its overhead. So we propose QVM, which is the system to leverage this gate utilization for noisy intermediate scale quantum computers. And we were able to effectively double the depth and width of quantum circuits to run on these QPUs. So feel free to check out the code. It's on GitHub, and also our ongoing research to further reduce this virtualization overhead with tensor networks. Thank you.
All right, thank you. Questions?
I think you might have preempted the question with the last line as well. So are you guys looking at basically calculating entanglement in different places to reduce the figure out a better way of doing dependency analysis or something like that? Or are you trying other things as well with it, is I think my question.
I mean, the technique itself is independent of entanglement, but I think it's kind of looking at how kind of interconnected some subparts of the circuit are, which, I mean, it's kind of the same as entanglement if you have normal circuits, but yeah, that's what we're doing.
Yeah, that makes sense. Yeah, that's why I was like, oh, are you using tensor networks for dependency analysis or something else as well?
Yes.
Thank you.
Could you talk a little bit about the benchmarks you were running against? Because it's, as I understand this, highly entangled connected circuits would be very hard to virtualize because you would have to virtualize a lot of gates to split them across. So can you talk about both the benchmarks that you used and the limitations of the technique?
So yeah, as I said, these benchmarks were used, the NISQ benchmarks, which are not as highly entangled as they're for those noisy QPUs. So their virtualization works quite well, but of course if you have like a QFT interconnected all the way, then this would not work for scaling it too much. So it works quite well if you have, for circuit cutting, to have circuits that have some very highly interconnected part, and between them they're not as interconnected. So for this it works perfectly. Also for this application where you have just linear entanglement sometimes or something like that. So there it works, but it doesn't solve fault tolerant algorithms.
But when you say NISC, you're not thinking of like these random circuit experiments, because I think those also leverage a lot of entanglement.
Yeah, probably if you have too much going on, then it wouldn't work.
Okay.
Thanks for this nice talk. I was wondering if it is possible to combine your techniques with quantum multiprogramming. So here you are considering when you are executing a large quantum circuit, you cut it into smaller ones that can be executable. So there are also cases where you want to execute many small quantum circuits on a large quantum computer. Do you think it is possible to combine these two techniques to handle different cases?
Yes, definitely. So I haven't looked at this in this work, but in case you can implement your scheduler to also schedule through this sub-circuit onto the same QPU. And we have also looked at this at another work in a quantum operating system that we did, which is at OSDI this year. So
very cool.
All right, let's thank our speaker again.
Thank you.